Hello, in this video we are looking at set notation, the intersection, the union, the conditional probability, as well as mutually exclusive and independent event rules. Okay, so this is where we start with set notation. They're not circles, but I'll be calling them circles. So imagine we've got two circles, A and B, A on the left with B on the right. So the probability of A is everything inside the A circle, including the intersection. Top right, we've got the probability of not A. That's what the apostrophe means. So that's everything else that isn't A that is coloured in. Bottom left, we've got the intersection of A and B, i.e. where A and B overlap. And bottom right, we've got the union of A and B, which is A and or B. So all of A is coloured in, all of B is coloured in, and the only thing that isn't coloured in is anything that isn't in A and or B. In general, when we have two circles, an intersection is one of the regions, a union is three of the regions. The union symbol looks like a U. The intersection symbol looks a bit like an N, I guess, which is the second letter of intersection. It is also the second letter of union, so ignore that. But union symbol looks like a U. So we've now added a diagram with G and H circles, the numbers 35, 15, 21, and 49. And then we're working out the probabilities at the bottom left. So the probability of G, the numerator is the 35 plus the 15 that are in the circle G, and then the denominator, as it is for all the other ones on this screen, is the sum of all the numbers. 35 plus 15 plus 21 plus 49 is 120. The probability of not G is the 21 and the 49 added up on the numerator, with 120 on the denominator. Of course, you could just take away the probability of G from 1 to get the probability of not G. Bottom left, we have the intersection. We can see straight from the diagram that the intersection is 15. And again, the denominator is 120. And then finally, the union is the sum of the 35, the 15, and the 21, which is 71, again, over 120. Or we could just take away 49 from 120 to get our 71. So our standard intersection is the one at the top left. Okay, the intersection of A and B, and as I said earlier, that tends to be one region, okay, especially with our two circle diagrams. But there are three other possibilities. We could have the intersection of A and not B, or not A and not B, or not A and B. And in each case, as you can see, one region has been coloured in. For the top right, A intersection not B, it's the bit that's in A but not in B. Bottom right, it's the bit that's in B but not in A. And bottom left, it's the bit that's in neither A nor B, i.e. everything else. Okay, so here we have the probabilities of all the different possible intersections. Okay, so top left we already know is 15 over 120 for the probability of G intersection H. Top right, G intersection not H, that's the 35 that's in G but not in H. Not G intersection not H is the 49 that's in neither of them. And not G intersection H is the 21 that's in H but not in G. And again, they're all over 120 because that's the sum of all the numbers. So the union is the one that most people find most difficult. The union of A and B is the simplest. It's the A and B circles coloured in completion. But then we have the three others. So the union of A and not B will include everything that's in A and everything that's not in B all together. And the only bit that isn't coloured in is the bit that isn't in A but is in B. And as I mentioned earlier, with our union and our two circles, we have three regions coloured in. And you can see in each of these diagrams that three of the four regions have been coloured in. Bottom left, we have everything that's not in A, as well as everything that's not in B. And the only bit that's left over is the intersection of A and B. And then bottom right, we have everything that's not in A and everything that is in B. So the whole B circle is coloured in, and everything outside of A is coloured in. And the only bit that's left over is the bit that is in A but is not in B. So the probabilities again for G and H, the union is 71 because it's the 35, the 15 and the 21 added together. Again, all the denominators are 120. The top right, G union not H, we've got all the numbers in G, that's the 35 and the 15. All the numbers aren't in H, the 49 and the 35 again, but we don't add it twice, giving a total of 99 over 120. Alternatively, it's everything that's not 21. Bottom left, we've got the probability of not G union not H. So the numbers that aren't in G are the 21 and the 49. The numbers that aren't in H are the 35 and the 49 again, but we don't count the 49 twice. adding up to 105 out of 120. Again, we could just take away the 15 from the 120, the 15 being the only number that's not included. And then finally, the probability of not G union H, we want the numbers that aren't in G, that's the 21 and the 49. The numbers that are in H, that's the 15 and the 21 again, but we don't include the 21 twice. So 15 plus 21 plus 49 is 85. Alternatively, those three regions are everything apart from the 35 that is in G but isn't in H. Okay, I've mentioned so far how you might work out some unions by taking away the bits that you don't want. And we can do something similar when we're comparing the intersections and the unions. So take, for example, the probability of G intersection not H, which is 35 over 120. And if we compare that with the probability of not G union H, which is 85 over 120, they are complementary. They add up to 1. And if you look at the notation, G intersection not H turns into not G union H, obviously by changing the symbol from intersection to union, but also by transposing apostrophes. So if you've got a G, it turns into a not G. If you've got a not H, it turns into an H. And you can do that with all four possibilities. So for example, if you look at the bottom left of the intersections, the probability of not G intersection not H is 49 over 120. The opposite of that is 71 over 120, which is G union H. So the not G turned into a G, and the not H has turned into an H, as well as the intersection turning into a union. And of course, you can do that in both directions. Okay, so now we're going to look at two rules. The rules for mutually exclusive events and for independent events. They are both rules related to the intersection. For mutually exclusive events, which are events that cannot occur at the same time, the rule is very simple. The intersection is 0, i.e. it does not exist, because if it did exist, it would imply that there's a possibility of both of them happening at once. So as a Venn diagram, we can't use our A, B or GH examples because they all had overlaps. So I've gone for a J and K example. We've got 3 in J, 4 in K, 9 outside, but the important thing is that the circles do not overlap. And that means that J and K are mutually exclusive. They can't both occur. One of them could occur, or it could be that neither of them that occur if it's that 9. Okay, but they both can't occur simultaneously. Independent events can both occur, but they occur independently of each other, as the name suggests. So one event has no influence over the other event. And the rule for that is that the intersection of A and B is the same as the product, what you get when you multiply the probabilities of A and B. If you draw a Venn diagram at random, it's quite unlikely to show two independent events, okay, because the rule is quite specific. Our G and H Venn diagram does show independence, and here's why. So the probability of G is 50 over 120, as we know, which cancels down to 5/12. The probability of H is 36 over 120, which cancels down to 3/10. And if we multiply those together, we get 15 over 120, which cancels down to 1/8. But if you just work out the intersection by looking at it, it's 15 again over 120, which is also, of course, 1/8. So they both give you 15 120ths, both of which are 1/8. So since the probability of G intersection H is the same as what you get when you multiply the individual probabilities of G and H, that tells us that they are independent events. Okay, there's another rule for independence, which I'll mention later, which relates to conditional probability, and we're going to look at the symbol notation for conditional probability right now. So the probability of A given B is written as this: probability of A vertical line B. Okay, so it implies that B is a given event. It's already known. We know that's happened. It's like if we had a bag with 3 red buttons and 4 blue buttons. If we take out a blue button first and then ask what's the probability of getting a red button, well, it obviously depends on what the color of the first button was, if we haven't got it back. If we know it's blue, then that's going to change it from if we didn't actually know what it was. So far, all our denominators have been over 120 using the types of notation we've been looking at, whereas now with conditional probability, the denominator will not necessarily, it won't be 120 because we're looking at a subset of the data. So for the first one, the probability of G given H, we start off with the fact that we're doing it out of H. We know that H exists already. So out of the 36, the question is saying, what is the probability of G? And in the H circle, 15 of them are also in G, so the probability is 15 over 36. The probability of H given G is not the same. However, having said that, the numerator will be the same because it is the same 15. But the probability of H given G means that we're starting off by knowing that G is the circle of interest. That's got a 35 and a 15 in it, of which 15 are also in H. So it's 15 over 50. So notice not only are the denominators not 120, they're also not the same as each other for G given H and H given G, but the numerators are the same because they're referring to the same 15 in this case. Finally, the probability of not H given G, again we're starting off with G, so we've got the same denominator as when we did H given G, or 50, but this time when we're looking at not H given G, we're looking at the 35 and the 15, but we want the 35 because they're not in H. Okay, so in the previous question we wanted the 15 because they were in H as well as G. Now we want the ones that aren't in H as well as G, so 35 over 50. Just to finish off, we're going to look at one final Venn diagram with U and V and just practice these 6 examples of notation. They're all empty at the moment. If you want to pause the video and work them out for yourself first, have a go. So for the first 3, the probability of not V is 11 over 17. If you look at the Venn diagram, I've coloured it in. Okay, so the total of all the numbers, 8, 4, 2 and 3 is 17, but the numbers we want are the ones I've shaded in yellow, the 8 and the 3 that aren't in V. For the probability of not U intersection V, we still want the 17 in total, but we want one region of our Venn diagram. It's the region that's not in U but is in V, and again I've coloured it in yellow, it's the 2, so it's 2/17. And then for our union, the union of U and not V, we want the numbers that are in U, that's the 8 and the 4. We want the numbers that aren't in V, that's the 8 and the 3, but we don't count the 8 twice. 8 plus 4 plus 3, the ones coloured in yellow, is 15, again out of the total of 17. One other thing to notice, I've already mentioned it, but I'll mention it again. If you look at the not U intersection V and the U union not V, they are opposites of one another. The intersection has turned into a union, the not U has turned into a U, the V has turned into not V, and the probabilities add up to 1. And finally, we have our conditional probabilities. So I've used a different colouring system here. So for the probability of U given V, I have coloured in the V, the bit that we know we already have, which is 6, of which we want the U's, of which we know there are 4 in that circle which is coloured in. So the probability is 4 over 6. For the probability of V given U, however, we are now looking at the U circle to start off with. That's the 8 and the 4, making the 12, of which it's the same 4 that are in V as were before for the numerator of the previous question. So 4/12. And then for the probability of not U given not V, I've coloured in not V as pink. That's the 8 and the 3. And of those, the ones that also aren't in U are the 3. So 11 on the denominator and 3 on the numerator. Thank you very much.